So this is what we have been discussing. We just started this Martensite transformation topic, and as I said in the previous lecture, there are few terms that you need to get familiar with respect to the Martensite transformation, and these are those terms that we have listed out over here. And I hope by now from the previous lecture you have some idea about this, the shape deformation that we were talking about in the previous lecture. Okay, so this is basically coming across because of the displacive kind of mechanism that you have in a Martensite reaction which is taking place without diffusion. Okay, so it's a simple change from one structure to another crystal structure without movement of atoms by diffusion. Okay, so when you do that, we have seen that there is some kind of shape change associated with that, and that is what we are calling as the shape deformation here in this kind of transformations. Okay, now as I said before, you also need to understand as to how this structure from FCC changing to body centered tetragonal BCT. Okay, so this is the austenite which is transforming, and this is the Martensite phase having a BCT structure which is forming because of this transformation. Okay, so in order to understand this particular change of crystal structure from FCC to BCT, you need to take the help of a concept or a kind of deformation or distortion known as Bain deformation or Bain distortion. If you want to understand this as to what do you mean by this Bain distortion, you actually have to look at the FCC lattice in a different way, because in a 3D structure of a crystal lattice, you can look at the arrangement from different perspectives. Okay, conventionally how we look at FCC is that the corners are filled with a particular type of atom, right? The atoms occupy the corners of this unit cell, and the centers of the faces of this cube, right? So this is how we have seen or we look at FCC structure, right? But can we not sketch out something else out of the same structure which does not look like an FCC? For example, if I extend this to another unit cell, the next one if I draw, can we draw some unit cell in this manner inside these two unit cells of FCC? For example, if I do like this, can we not sketch out something like this within the same unit cell? Okay. This particular unit cell, let me color it differently for you to understand. Can we sketch out a cell like this? We can, because you can see it, we can draw it inside the FCC unit cell itself, right? But does it look like an FCC? It does not, okay? So if we just take it out, let me try and draw it outside over here somewhere, okay? Where are the atoms here in this cell that we have taken out now? And there is one more which is coming from this face, no? This face centered atom which is here is coming in the body center of this, right? But the C by A, that is the vertical axis, and these two axes over here, you know, the X, Y and Z axis, these are not equal. In the case of the FCC lattice, these are equal. A equals to B equals to C, right? X, Y and Z direction vectors are equal. We know that. But here this C by A is not 1, right? If this is C, which means that this is basically a tetragonal lattice, which we could sketch out from the FCC unit cell. Okay, so if we do like this in this manner, we see that it is a BCT structure which is coming out, because at the center you have an atom at the center of the body. The body center has an atom, and this is coming out as a tetragonal cell, and therefore this structure is body centered tetragonal, BCT. Okay. So C by A is not equal to 1 here. If you calculate, you can easily find out that C by A will be around 1.4. How is that? Because we know these two is going to be A by root 2, isn't it? These two sides that you have, this A1 and A2, okay, these are basically A by root 2, and C we know is equal to actually A, where A is the lattice parameter for the FCC unit cell. Okay. So C by A, then you can calculate, will come out to be 1.4. Okay. I want to do something else here just to understand what is the meaning of Bain distortion. Okay. So this is not enough right now to bring out the distortion that we are talking about, right? Because we have here, we have simply taken out a different unit cell from the FCC unit cell, which is coming out as a BCT, but we still do not know from where the distortion is coming out that we have been talking about. Okay. What I have done here is, in this second diagram over here, I have given a compression along the C axis and an extension along A and B. Okay, so just try and understand what I am trying to say here to bring out the Bain distortion. Okay, so if I just compress it along the C axis and allow it to expand along the other two axes, the A1 and A2 or A and B, then it would take up a structure where the C by A ratio is still more than 1. So if I do that way and give a compression of about 17% along C axis and an extension of about 12% along A and B axis, it will take up a BCT structure which is having some C by A ratio, let's say in the range of 1.045, something that you find in the Martensite structure. Okay, so this is not cubic. The C by A ratio is not 1. Okay, so this would of course depend on the concentration of carbon. This is basically given by this particular equation, the C by A ratio. Xc is the carbon concentration, and why it is dependent on the carbon concentration, that would also be clear as we go along. Okay, so if we take about 1% carbon, you see that the C by A ratio becomes 1.045. Okay, now if I do little bit more compression along the C axis, this C by A would come down to 1, isn't it? So it is close to BCC in that sense. It was going to BCC, but somehow it has stopped in between. Why it has stopped? Because we have not allowed the diffusion to occur. If we allow austenite to change to another structure at lower temperature, it would go to ferrite, the BCC. But as I said here, we did not allow that because we are having the transformation at a temperature where diffusion cannot occur, is very difficult to occur, and therefore it has stopped somewhere in between with C by A ratio little more than 1, but not 1. Okay, so that is how this structure change comes about here from the FCC to the BCT. But try and understand as to what is happening to the lattice, because you are changing the structure by compressing it down the C axis and letting it extend along the other two axes, right? So it is actually creating some kind of strain, some kind of distortion that you see over here. So this kind of homogeneous distortion, if I now try and come back to this Bain strain and define it, so as I said, there is a distortion when this kind of change is occurring from one crystal structure to another crystal structure by some compression or extension along the crystal axis. Okay, so a homogeneous distortion of that kind, which leads to a change in the crystal structure by compression or extension along the crystal axis, is known as a Bain distortion. And this is relevant to Martensite transformation because this kind of change in the crystal structure you see without any change in the composition, right? So by diffusionless, what you mean is that the composition of the austenite in terms of the carbon content is not changing. It is simply changing from one crystal structure, that is FCC, to another crystal structure, that is BCT. And in this change you could see there is a distortion involved, and that kind of distortion which leads to a change in the crystal structure goes by the name Bain distortion. Okay, so it is named after that person who proposed this theory, Edgar Bain. Okay, so we are talking about the same mechanism, that is the displacive mechanism here, which does not involve diffusion. Okay, so right now let us try and understand as to where is the carbon and what is the role of the carbon here in this particular distortion, because we have said that the C by A ratio depends on the carbon concentration, okay, in this manner through this particular equation over here. Okay, can you point out the location of the carbon in this unit cell? Do you remember when we discussed the crystal structure of these iron carbon alloys, the austenite and the ferrite? We discussed where the carbon actually sits, isn't it? We know where the carbon is located. It is basically the octahedral voids, right, where the carbon would sit. Where are the voids in the FCC lattice? It is at the body center and the center of the edges. Okay. So if I draw the carbon atom as a black circle here, it is there here around this center, right, the center of the unit cell, and it is also there at the edges, the center of the edge. Yeah, so I'll just draw the carbon atoms by a dark circle. This is the edge of the center of one of the edges, and the center of it will have a carbon atom. Similarly, all other edges will also have this one, then at the center of this, and so on. And you also had one at the body center. So now can we bring the carbon atoms in this BCT cell? Okay. So you can see that along the C axis, the carbon of the austenite is retained in the same manner. Okay. Now these voids along the C axis, the chances of occupying those positions by carbon would increase as you increase the carbon content. It is not that all these voids will be filled with carbon. It depends on the carbon concentration as to how much of these voids will be occupied by carbon. As you increase the carbon content, the chances of occupation of these voids will increase, right. So therefore, when you increase the carbon content, the chances of voids being filled along the C axis will also increase. And if you have presence of carbon along the C axis, compressing it along that axis will be difficult, right. And therefore, as you increase the carbon content, the C would increase, as you could see from this particular equation, right. So this goes to again the same concept that we talked about as to how the BCT structure is coming out from the FCC. And now if you put the location of the carbon atoms, you could easily correlate as to why the C by A ratio would depend on the carbon content, right, because the carbon of the austenite is still sitting along the C axis of the BCT cell also. So this is one theory, which you may not find in all the books. Most of the time people talk about Martensite saying that it's a diffusionless process and it goes by change of one crystal structure from FCC to BCT, and the buck stops there. Nobody tries and explains as to how exactly this happens. If you go about this theory that I'm presenting right now, you would see that all the characteristics of the Martensite can be beautifully explained. This is one of them, of course, as to why the C by A ratio settles down around those values and why it changes with carbon content. That is just one small aspect of it. There are many more when you talk about Martensite, you would find characteristics which are very unique, right? And all those characteristics can be explained by the theory that we are going to see in this class. Okay. So today I think this is all we have. We have understood so far these two aspects that we have listed out before, the shape deformation and the Bain distortion. Okay. These two basically form the basis of this entire Martensite transformation, right? We have understood why there is a shape deformation, to start with, and then we have also understood as to how that distortion or deformation comes about in case of the Martensite transformation with the help of this concept known as Bain distortion. Okay. Now, as we go about it, as to how this Bain distortion ultimately leads to the Martensite structure and try and understand what happens after this, as I said, we will be able to understand all the characteristics of the Martensite phase. It is not only about the structure change. Okay. The way the structure change occurs here, or way the phase forms without any diffusion, has a lot of bearing on the structure and also the properties of this phase. Okay, so all those can be beautifully explained if you go about this theory, as I said, and we will see all that as we go along. Okay, so today I will stop here, and then we'll come back to it again to discuss the other aspects.